Okay, first of all, thank you very much for inviting me for this event. It's a pleasure and honor for me to give a presentation. And as a previous speaker, I also will be talking about polarimetric observation, specifically about using multi-angular satellite polarimetry for characterizing Earth atmosphere and specifically atmospheric aerosol. And, atmospheric aerosol, it's just to see a few illustrations above, it's like smoke, pollution, dust, sea salt, and so on. And it's a very important component in the atmospheric climate and environmental system. What I'm talking about, it's about multi-angular polarimetric observation. When from space, we observe a state of reflected radiation, polarimetric state of reflected radiation at different angles. And this type of observation considered as one of probably most powerful passive observation for monitoring atmospheric particulate pollution. And here I just showed you some illustration of most known missions. And also I presented you like list of missions which already were in space, which are now, and the mission which you see in future. The basic idea is that although we had some polarimetric mission, it was not so many. Probably the longest was Polder 3 on the Parasol mission, which is flight for 9 years, which was French-US mission. And but this mission showed that it's really promising observation. There was number of efforts which are successful to launch more polarimeters, and we have now few in space, but still pretty recently. But the main point is that in future, probably monitoring of aerosol properties will heavily rely on this multi-angular polarimetry observation. And why is that? Because, well, if you look at the theoretical description on the interaction of electromagnetic light with objects in the atmosphere, like particles in the air, it's the electromagnetic radiation described fully by Stokes vector, has 4 elements. And the interaction with any object described by scattering matrix, which you could see here. And this scattering matrix, it has 16 elements. However, for particles with rotational symmetry, there are only 6 elements which are independent, which you could see here. And evidently, these elements, as long as we can characterize them, I mean, measure them, the better we measure them, the better information we have. And here, just quick illustration that element P11 here, it's described basically intensity of the reflected light, and it's sensitive to the shape of size of objects, shape, absorption property, refraction, and so on. This means all important properties of atmospheric aerosol. But 5 other elements characterize state of polarization, which provide evidently even more detailed properties of optical properties of all atmospheric aerosol and other objects, because aerosol is not the only one. And now, if you look at geometries, geometry of different observation of remote sensing observation of the atmosphere, you can understand why multi-angular polarimetry is so important. For example, on the left, you see in principle angular coverage of different ground-based or in situ observation. Only those observations allow, like from nephelometer, measure entire scattering matrix. But it's very local observation, and it's not enough to characterize the global distribution. Well, ground-based photometry, like, for example, those instruments from Ironet, they are they measure both two elements, like sensitive to two elements, P11 and P12, in mainly forward hemisphere. This is quite a lot of information. However, this also instrument, they have only local coverage. In that sense, if we look at satellite measurements, for example, right now, MODIS-like measurements, it's single view radiometric measurements, most popular for characterizing aerosol. These kind of measurements observe only one point in the angular distribution of scattering matrix, only for first element, which is phase matrix. In that sense, multi-angular polarimeter, for example, like Polder, they observe first element P11 and second P12 in pretty wide range of scattering angles in back hemisphere, and evidently they are much more sensitive to the aerosol properties. That's the main point. Now, I showed you that polarimetric observation only sensitive to the first two elements, and evidently you may have question, what about the rest? So much information lost. But if you look and write carefully the equation of radiative transfer equations, which describe transfer of energy in the atmosphere, you would see that due to the fact that source of our light source for our observation is the sun radiation, which is non-polarized. That means Stokes vector has only I measurements equal 1, and the Q, U, and V equal 0. And once we take this into account, we will see, like here in the equation, that both intensity and the bottom intensity and polarization are affected only this by two first elements, like intensity only by phase function element F11, and the polarization basically only degree of linear polarization depending of element 1, 2, and 1, 1. That's in that respect, actually these elements are, I mean, measurements of multi-angle polarimeter sensitive to these elements, which is very important. Now, in order to account really carefully for all interaction in the atmosphere, we should understand that the radiation which we see affected by many different components of aerosol, and we have to account for multiple scattering effects, which include scattering by different scattering and multiple interaction of the scattering from aerosol particles, interaction with molecular scattering due to a fluctuation of air density. We should account for gaseous absorption as well as surface reflection. For example, we heard in previous presentation where surface was main object. And one of the main difficulties of all satellite observation of the atmosphere, it's really to distinguish surface and aerosol contribution in order to characterize atmosphere. And in that sense, polarization add quite important information. For example, here, this is just calculation of the satellite signal of intensity over bright sizes and polarization. In OSM, it's like over desert. And here on the left, you see the black line. It's basically BRDF, bidirectional reflectance of the surface, black line, and two line, blue and red. It's a contribution of fine and coarse mode of aerosol. You could see here on the left size distribution. And you could see that satellite observation in that area would be dominated by surface. So it's very difficult to see aerosol. But once we look at polarization, situation changed, because in fact the surface mainly does not polarize a light. And this is why we see that, for example, fine particles of biomass burning dominate in that range already. For dust particles, we also see that it's kind of stronger signal than a soft surface, but not that much. And so that's means for large particles, this factor is not as important, and I will explain you why a little bit more. But here, I just wanted to show you that based on a general consideration, multi-angular polarimetry is very promising because we make measurements of a lot of characteristics, and therefore it seems like we can characterize a lot of parameters. However, during probably nearly 20 years, when we have these measurements, we community realized that although potential is high, to get most benefit from this potential is difficult because you need to apply very complex algorithms, which are different than from MODIS. For example, computational time is become an issue because you need to account for all different small effects, and it's take time. And we have a lot of data in satellite images. And then there are additional uncertainties. That means we have sensitivity to many more parameters, but we need to make assumption about even more other parameters which could be neglected in just the intensity observation, for example, vertical distribution. And this is why, in spite of we had already in past several missions, the multi-angular polarimetry did not show really huge outcome in sense of observation. And one of limitations were algorithm. And here I'm just presenting our algorithm, which is called GRASP, Generalized Retrieval of Atmosphere and Surface Properties, which is was developed specifically for the this polarimetric observation. Actually, it's very versatile algorithm, can be applied to many observations, but the more complex observation, the more efficient algorithm is. And in that sense, multi-angular polarimetry data are very good. I mean, very actually very appropriate for that. And the main concept of this algorithm, that we have two independent models, forward model and inversion model, and they are developed in very rigorous and very fundamentally rigorous way. And this is important for characterization of all for characterizing of observation from all complex remote sensing observation. Here, just a quick description of our forward model, which is one of main features. It's modular, and it describes many different effects. And modular mean that we can replace this model and improve them independently. For example, in the system where we look at aerosol, surface reflectance, and gas absorption, we have several models for like describing only aerosol single scattering properties like total extinction, absorption, full phase matrix, and also, if necessary, vertical distribution. We have the same for gaseous absorption and surface reflectance, where we also describe BRDF and also BPDF, bidirectional polarized surface reflectance, as also was discussed in previous talks. And then we account for all multiple scattering effects. And as a result, we can simulate any remote sensing observation in the atmosphere. Yeah. And this is how we describe aerosol. Aerosol is very, very complex mixture because particles of aerosol can be different shape, morphologies, sizes, and so on. And if you look at here at small illustration, you would say how we can do it. But in fact, even a relatively simple model managed to describe main optical properties of aerosol. And here you see that we model aerosol as a mixture of multi-component mixture of aerosol of different origin, which can be spherical and non-spherical, described by randomly oriented spheroids. And here you could see that, well, each fraction characterizes kind of three-dimensional set of parameters: size distribution, shape distribution, and height distribution. And I just wanted to mention you that non-sphericity is a very important aspect which need to be accounted in remote sensing of multi-angular polarimetric remote sensing. And here I wanted just to mention my friend Michael Mishenko, who unfortunately passed away several years ago, kind of unexpectedly, prematurely. But anyway, with a collaboration with him and also with Pinyang, Brent Holban, and here you see Tatiana Lapionak, we developed the model for accounting particle non-sphericity using randomly oriented spheroids. You could see how it works. And although spheroids is very simplest non-spherical shape, it seems like simplified, but nonetheless, in reality, it's worked well. You could see that here is the phase function and a degree of linear polarization for different spheroidal shape with different aspect ratio. And once we average over size and different shapes, we get these smooth curves. And you could see how spherical particles, which are usually used as a base model for as well, scatter differently with non-spherical particles. And here you could see, and that's, you could see how important accounting for non-sphericity. For example, this is a degree of linear polarization for spherical particles and non-spherical particles. For coarse mode, for different refractive index, you see that they are very different. And also one of the observations that actually once particle non-spherical will lose sensitivity to many parameters. So in that sense, the polarization may be less promising than it's expected using spherical particles. Although this is a bit, let's say, disappointing, but nonetheless, it's good to understand that and don't over-expect, at least in this respect, from the polarimetric observation. Another thing that we have to really use a rigorous inversion algorithm, because we need to deal with many, many parameters. And that cannot be neglected in any remote sensing, complex remote sensing observation. In that sense, we develop multi-source least square method approach. And I just will say a few words about that. Like, for example, if you have single sensor data, everyone knows, or most of people know, least square approach, which probably not challenged by anyone, that it's a good one. But when we talk about multi-source least square, we just make a small step further. We know that, for example, if we have several sensors, we can observe, we can obtain statistically independent observation. Spin covariance matrix has this array structure. And then from this equation, we can get from this multi-term least square method. And one of feature of this method that we can really simplify utilization of a priori information. For example, if instead of second sensor, we think that we know some information directly about parameters, we can get this optimal estimation method by Clive Rogers, which is widely known. But even more importantly, that we can use multiple a priori constraints. For example, in GRASP, we use many more. For example, direct a priori estimation, also a priori smoothness restriction on the retrieve functions and so on. And then even for this freak type of observation, well, including also measurements, we can get this equation, which already hardly can be reduced to optimal estimation, but nonetheless, they are so very practical, and you could set up very complex algorithms like GRASP. If you look a bit more, you would see that we have much more complex fitting structures than most of algorithms. And here, just illustration that developing this GRASP, we were able to process polder mission all 9 years and derive parameters. You could see what we can derive. It's the total optical thickness and Strom exponent, the parameter characterizing size, single scattering albedo absorption, height, and so on. So basically, we retrieve many more parameters, which is then it's retrieved from a conventional MODIS observation. You could see other illustration like this ocean land. It's winter 2009. This is how we see aerosol with our data. And we also see very well surface, but I don't have time to show that. And here you just could see the global validation of this observation against our net size. You could see we can get total optical thickness, more, and even on Strom exponent, which already characterize the result type, and also optical thickness of fine and coarse mode, which is also very important. These three parameters we basically don't see from MODIS. And what does it give? For example, here you could see like winter and spring in Africa. And this is total optical thickness. You see that we see same place, different period, and kind of globally similar features. But we see the optical thickness. And this kind of optical thickness we see not only from polarimetric data, but also from like MODIS-like. And here just validation of models or of our retrieval against AeroNet, compare how it's done from MODIS. And on the right, it's just correlation of total optical thickness of MODIS with parasol data over ocean. You see the agreement very good. So in that sense, in total optical thickness, we probably bring a bit more accuracy, but not so much. However, now if you look, if it's similar aerosol, looking at MODIS data, you would hardly say something. But looking at the Polder data, you could see that in winter, we see like yellow color. This means it's small particles, more like biomass burning. And while in spring, it's dominated by dust, blue color, that's mean Angstrom exponent small and particles are very large. And if you look, just as I said, at validation of this parameter globally, this is what we see on the left from Polder. From MODIS, we don't see that. And moreover, if we consider that Polder data provide most accurate information and compare globally over land, MODIS Angstrom exponent versus Angstrom exponent of Polder, you could see that while in Polder we see big variability, in MODIS evidently there are some models which are fixed and they basically not sensitive to any variation of this parameter, that's mean aerosol type. And that's feature not only MODIS, but any singular view observation. So this is why multi-angular polarimetry is quite important. And here, just quickly, I showed that for this kind of data, we can also use a grasp component approach, where we assume that aerosol is a mixture of particles of different origin. For example, fine modes like black carbon, brown carbon, water, and so on. And below, you just see that if we do that, we still retrieve all optical properties like optical thickness and Angstrom exponent, single-slit albedo, and we retrieve them well, even maybe better than with other approaches retrieving directly optical properties. But it's very important that in that case, we also have some information about different composition, distribution of aerosol of this different composition. Like, for example, here you could see illustration that we see where it's coarse dust, ferrum oxide, which characterize dust of different origin, absorption in black carbon, and so on. And this is new feature. And this is my last slide. And just in conclusion, I would like to say that multi-angular polarimetry is expected to bring important correction of aerosol climatology and other findings which are important for characterizing of atmospheric environment and climate. At the same time, I just, you probably understood from my presentation that we have to understand that there are a number of challenges which should be taken well into account. Like, we should deal with many parameters, we should use very capable models, and we should also look at more sophisticated assumption and constraints, which is sometimes very challenging. So, and I stop here. Thank you very much.